In the previous section, we looked at a way to compute the steady-state error of a system with respect to the reference input for the general case. And in this section, we are looking at the same idea, but for a very special case. And so I have a warning up front, and the warning is that the following method that we're going to look at here is a special case, and so please always use the appropriate method for the problem at hand. So the reason for this warning is that the method we're going to come up with for this special case is quite a bit easier, quite a bit more straightforward than the method we looked at before. And so the temptation is always to use the special case method when in fact it doesn't always apply. So we always have to check, does this method apply? If it does, great. It's easier, use it. If it does not apply, then you need to go back and use the method from section 4.7. This method is going to apply for the configuration that is known as unity feedback. And as a reminder, this is what a unity feedback system looks like. It's any kind of a feedback system where the feedback gain is exactly 1. The output y is compared to the reference input exactly to compute the error signal going into the open loop system, which might include the plant or the compensator and the plant together. If we're fortunate enough to have this situation, we have a simpler solution when we're looking for the steady-state error. But if there's any kind of dynamics in the feedback loop, as there often are when I've got some sensor in here, and the sensor might have some time constant or something like that, some filtering to it, if there's any dynamics in the feedback loop, then we do not have a unity feedback system, and we must use the more general rule from the previous section. So, warning aside, what we do in this case is we do exactly the same thing from the previous section, but we can substitute in the configuration of the unity feedback into all of those equations and come up with something that's a little bit simpler. So recognize here, probably you've done so many of these transfer functions by now that this is very routine, but the transfer function from R to Y for this system, the T of S, is equal to the G open loop over 1 plus G open loop of S. That's our closed loop transfer function there. And when we looked at finding the steady state error versus system type in the previous section, we said, okay, I've got to compute 1 minus T of S. Okay, so what we do is we first compute 1. This here is 1 with a compatible denominator for the subtraction, minus T of S, which is this. And we notice that in the numerator, I've got 1 plus G minus G, so the G's go away and I'm left with 1. And the denominator is 1 plus G open loop of S. So we conclude that the error is equal to 1 over 1 plus G open loop times R. So when we are looking at test inputs, just like we were before, that were unit steps, unit ramps, unit parabolas, and so forth, where the test input was R equals 1 over S to the power K plus 1, and we compute the steady state error. Steady state error is limit as S goes to 0 of S times E of S. That's going to be limit as S goes to 0 of S times E of S, 1 over 1 plus G open loop of S, times R of S, which is 1 over S to the K plus 1 power. And this S here cancels one of them there, and we're left with this. Okay, let's work with that. If the system is type 0, then we're going to have a constant error to a unit step input. And so we'll have steady state error is limit as S goes to 0 of 1 over 1 plus G open loop, and the S to the 0 power disappears. And in order to evaluate this error, what we need to do is we need to take the open loop transfer function of the system and plug in s equals 0, and that value that we get we call Kp, which is the position error constant, and the steady state error is simply 1 over 1 plus Kp. For a system that is type 0, if I try higher order inputs like ramps and parabolas, then the error will be infinite. So this is the error to a unit step. For a system that is type 1, then if I put in a unit step, I will get 0 error, but when I put in a unit ramp, then I need to evaluate this with k equal to 1 for system type 1. So I need to evaluate then the limit as s goes to 0 of 1 over 1 plus g of s, all multiplied by 1 over s. And notice that when I do that multiplication, the s times 1, this here would give me 1 over s plus s times g open loop of s. And as s goes to 0, this term goes to 0, and this term potentially does not. And so we define the velocity error constant of a system to be kv as the limit as s goes to 0 of s times g open loop of s, and that's all that's left in the denominator. So if this fraction here is not 0, then I have, in fact, a type 1 system. Not 0, not infinity. It's a type 1 system. For a system that's type 2, we do the same thing, except I've got 1 over s squared in there. The same kind of algebra applies, and I define an acceleration error constant is the limit as s goes to 0 of s squared times g open loop of s. And when I find all that value, that's the steady state error is 1 over the velocity acceleration error constant. This is much easier to evaluate than the general case rule, because I simply have to plug in different values into the G open loop. I have to plug in s equals 0 first, and if I get a non-zero, non-infinite number, then I've got a type 0 system. If not, then I keep on going. If I plug in s equals 0 to compute kv and I get a finite number, then I've got a type 1 system. If not, I keep on going, and so forth. It's easier, I think, than the test that we had to do in the previous section. So we have some formulas here, meaningful only for unity feedback. Again, please note this is a special case, and we have these limits, these 3 limiting cases that give us constants, which are position, velocity, and acceleration error constants. Then, for this case, we have steady state tracking errors for unity feedback case only, again highlighted, that if the system is type 0 and I have a step input, the error will be 1 over 1 plus kp for a step. It would be infinite for a ramp, infinite for a parabola. If the system is type 1, there will be 0 error for a step, 1 over kv for a ramp, and infinite for a parabola. And if it's a type 2, 0 for a step, 0 for a ramp, and 1 over ka for a parabola, for example. Let's do some examples. Let's look at open loop g of s equal to s plus 1 over s plus 2, s plus 3. What's the system type? Well, first thing is plug in 0 for s. And when I do that, my numerator is 1, my denominator is 2 times 3. My overall result is 1/6, which is neither 0 nor infinity. And so we're done. We have found kp, and the system type is 0. And the steady state error to a unit step is 1 over 1 plus kp, or 1 over 1 plus a sixth, which is 6/7 overall. Second example, consider this G-open loop of S. We try first what happens when I plug in S equals 0. And when I do that, I get my numerator. Okay, that goes to 0, that's 0, that's 0. Denominator, that's 0, that's 0, but that's 0 and that's 0. So the numerator is 1 times 10 times minus 5, but the denominator, this whole term is 0, and so my denominator is 0, and I get infinity. And if you look at the steady state error, this is Kp. My steady state error is 1 over 1 plus Kp equals 1 over infinity equals 0. So there's no steady state error to a unit step for this system. So it can't be a type 0. It must be at least a type 1. So let's try the next one. Let's evaluate S times G of S. And when we do that, we notice that there's a factor of S in here that can be canceled, and it has been canceled when I've written it out here. So I've multiplied that whole thing by S, it cancels that S in the denominator. Now when I put in S equals 0, I've got that going away, that, and that. My numerator is 1 times 10 times minus 5, which is minus 50. The denominator is 3 times 1, which is 3. And so I have a velocity error constant of minus 50 over 3 and a steady state error to a unit ramp of minus 3 over 50, and it's a type 1 system. Let's try one more example. Consider this open loop G of S. I've got S squared plus 2S plus 1 over S to the 4 plus 3S cubed plus 2S squared. And I want to know what is the system type. So first thing I do is I plug in S equals 0. And I notice that the denominator is 0 immediately. So I would have an infinite result. The type must be bigger than 0. I multiply by S. And notice that the denominator has a factor of S squared that can be pulled out. So this is equal to S squared times S squared plus 3S plus 2. So even if I multiply by S, I'm still going to have an S in the denominator, and I'm still going to have a divide by 0. And so I must have a type that's bigger than 1. Last thing I try is I try seeing what the acceleration error constant is. I multiply by S squared. Which cancels that S squared and leaves everything left. And so I have S squared plus 2S plus 1 in the numerator still, S squared plus 3S plus 2 in the denominator. And when I plug in S equals 0 in the limit, those go away, and I have 1/2. So the acceleration error constant is 1/2. The system is therefore type 2. And the error to the unit parabola is 1 over 1/2, or 2. So the approach, I think, is a little bit easier if we do happen to have a unity feedback system. And what's interesting about this, and this is a key point here, and it's a key point in a lot of places, when we have unity feedback systems, as much as we can, we're going to develop tools that use the open loop transfer function to tell us something about the closed loop response. So here, the open loop transfer function is telling us about the closed loop steady state response without having to compute the closed loop transfer function itself and manipulate it and use that. So I can use what I'm given without a lot of math and get a value that I'm interested in. Another thing that you may have noticed as we went along in the example is that for unity feedback systems, the number of poles in the original transfer function at the origin is equal to the system type. Let's go back to example 1 here. Example 1, if I plot the poles and zeros of this, I've got a pole at -2, a pole at -3, and a 0 at -1. I don't have any pole at the origin, and the system type is 0. In this second case, it wasn't maybe quite as obvious the way I wrote it, but when we factored it out, we saw that in the denominator, that s squared plus 3s was really s times s plus 3. So I have a pole at s equals 0, a pole at minus 3, and wherever the poles of this end up being, and honestly, I don't know. But I do have one pole at the origin, and it's a type 1 system. In this final example here, I factored it out to s squared plus 3s plus 2. I've got 2 poles at the origin, and this factors to 1 pole at minus 1 and 1 pole at minus 2, I believe. But the key point is that there's 2 poles at the origin, and it's a type 2 system. So the really, really easy thing about unity feedback systems, if all you want is the system type and you don't particularly care for knowing what the value of the steady state error is, all you have to do is count the number of poles of the open loop transfer function at s equals 0. That's your system type. But again, that's only for the unity feedback case. That does not apply in the general case, so please be careful. I'll do another example here. This is a DC motor with proportional control, so we've seen this transfer function before. This is the motor transfer function, and then our controller transfer function is simply D equals K sub P. So is this a unity feedback system? Well, it doesn't look exactly the same as what we saw before because there's 2 boxes in the feed-forward loop, not 1, but we can combine these, and if we combine those, we get one transfer function, which is this, and then the box does look the same. So all of this would be G open loop of S. So for unity feedback, the important thing is not the number of boxes in the picture, but the important thing is that the feedback from Y to this summation is just a wire. It's just a feedback of 1. Looking at that transfer function, the open loop transfer function, I've got a real pole not at 0 and another real pole not at 0. So this is a type 0 system because there's no poles at the origin. The steady state error, we figure out, well, what is the position error constant? So that's equal to G open loop of S at S equals 0. So plug in S equals 0, that term goes away, that term goes away. I have KPA, and we say that for this case, the steady state error is 1 over 1 plus the limit as S goes to 0 of the G open loop, which is that. And we get a steady state error that agrees with the prior results of this example. Let's do the example again with, instead of a proportional controller, we have a proportional integral controller. So D of S now is Kp times 1 plus 1 over Ti times S. And then combining the controller and the plant together, we have this open loop transfer function. And it might be helpful if we rewrite it. Let's multiply top and bottom by TIS, and that's going to be equal to TIS times KPA plus KPA over TIS, tau 1s plus 1, tau 2s plus 1. Notice that I do have a pole at the origin, so this is going to be a type 1 system. If I didn't notice that and just plugged away, I could plug in S equals 0, and I would find out that my position error constant is infinity, so I can't have a type 0 system. And then I can take the limit of S times D times G as S goes to 0 and find out that's not 0 and find out it's a type 1 system. but rewriting it made that more clear because I can see, oops, I've got one pole at the origin. This must, in fact, be a type 1 system. When I take that pole at the origin and multiply it by s, that goes away, and then s goes to 0, and here, and here, and here. And to find the velocity error constant, I just have kPa divided by ti is all that's left. And the error is 1 over the velocity error constant. And so it's 1 over that. So this is the velocity error constant, and this is the steady state error, which is 1 over that. One more example. And this is a DC motor with a 2-integrator controller. And all we've done is we've added a 1 over TIS squared to the previous controller and multiply D times G, and we get this. And again, we could put this over a denominator that shows more clearly what's happening. Multiply top and bottom by TIS squared. So I've got KPA TIS squared plus KPA times S plus KPA all over TI times S squared, tau 1 S plus 1, tau 2 S plus 1. When we write it that way, we see, oh, look, there's an S squared in the denominator, so there's 2 poles at the origin. This is a type 2 system, and in order to find what the acceleration error constant is, S goes to 0, makes that go away, that go away, that go away, that go away. The limit, multiplying in the limit makes that go away. So I have kPa over Ti as my acceleration error constant, and the steady state error is 1 over that, or just Ti over Kp times A. So this method is quite a bit easier, and maybe it shows now why we do integral control, or at least another way of viewing it. Because if the final transfer function of the closed-loop system satisfies the final value theorem, that is, if the final transfer function is stable, then adding the integrator in the open-loop transfer function adds poles at the origin and increases the system type and gets rid of the steady-state error. So that concludes our look at steady-state error from the perspective of minimizing the error with respect to the reference input. But there's one other source that could lead to steady-state error, and that's disturbance. And so we look at that next.